Hello. Today we will continue our discussion about the relationship between two quantitative variables, hopefully a linear relationship, but nonetheless it's about the relationship between two quantitative variables. But first, what I want to do is begin with some properties of the correlation coefficients. And it's called R, as you know. So this is the formula for R, which you never have to know or memorize or copy or anything of that sort. I wrote it just to explain this very briefly. Let's say your X values, the values under L1, is maybe your height in inches. So this would be observations in inches minus the mean in inches. That's still in inches. 5 inches minus 2 inches is 3 inches. If you divide that by the standard deviation in inches, the inches cancel. Now let's say Y is time in minutes, let's say. Minutes minus minutes is still minutes, and divide minutes by minutes, it goes away. So this quantity has no units, and this quantity has no units. And when you add quantities with no units, you'll end up with no units, and that's just a naked number. So R has no units. So you could say R is 0.7 with no units whatsoever, okay? So that's the first fact. Second, it goes without saying that the correlation coefficients, or the correlation, I should say, requires that both variables are quantitative. As a matter of fact, the relationship, the formula for R is this. And you're not going to be adding, you will never be able to add variables that are qualitative. It's silly. Okay, so both variables have to be quantitative. The correlation coefficient, or the correlation between two variables, does not differentiate between who is the X and who is the Y. Now, let me just say this quickly. So if I have values, okay, I have 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. Now, so this is X and this is Y. And I can easily find the equation of this line. Y is going to be X plus 1, I believe, right? Y equals X plus 1. Okay, now, if I decide to flip-flop these points, so now you have 3, 2, 5, 4, 7, 6. I can guarantee you that the new equation of the line, let's call it Y2, is not going to be X plus 1. And I can guarantee you that even the scatter plots will look something like this. I'll do it in red. 3, 2, 5, 4, and 7, 6. The line is different. The scatter plot is different, right? The points are different. 3, 2 is not the same thing as 2, 3. Everything is different except for R. Why? Because by definition, R measures the strength of the relationship between the variables X and Y. So you have the right to say R measures the strength of the relationship between X and Y, or between Y and X. It doesn't matter who you say first. I have a relationship with you, you have a relationship with me. The strength of that relationship doesn't change whether or not you know who is the explanatory variable and who is the response variable. Okay? So that's another thing. Actually, the formula can tell you that too. I'm glad I just saw that. If I flip-flop X and Y, so this will be Y I minus Y bar over S sub Y, and this will be Xi minus x bar over s sub x. Now you know that multiplication is commutative, right? A times b is the same thing as b times a. And that's just a silly number independent of x and y. So just from the formula, you know if you flip-flop x and y, everything will change except r. You also know that from the formula that the variables have to be quantitative. You also know from the formula that the correlation coefficient has no units. I'm actually glad I wrote this. It helped me with all these three facts, okay? Now, this one can be confusing. The correlation of values close to 1 or negative 1 does not imply a linear relationship. Now you might be pulling your hair because you heard me say that R is between negative 1 and 1. And you also heard me say that if R is in this region, let me put it this way. If I have a scatter plot like this, you know that R is close to 1. Close to 1. I don't know why I put negative 1. If you know that the scatter plot looks like this, you know that R is somewhere in here, maybe negative 0.9. And for this one here, maybe 0.96 or something, right? And you also know that if the scatter plots looks weird like this, most likely R is somewhere in here. You heard that. But then you heard me say the correlation of the values on the edges, on the endpoints of your interval, does not imply linear relationship. But I just said that if this looks fairly linear, R is going to be here. And if this looks fairly linear, R is going to be here. So what's the confusion here? The confusion is this. From logic, you know, if P, then Q, let's say this statement is true. Does it imply that the converse is true? The answer is no. No means not necessarily. For example, if I say to you that if x equals 2, what is x squared? I think all of you will say 4. And that is a true statement. Now, if I find the converse and I say if x squared equals 4, does it imply that x equals 2? You're going to say, yeah, it could be 2, but it could also be negative 2. So it's not always true, so we say false. The converse does not have to be true. What does that mean? It means the following. If the scatter plot looks linear, then definitely R is close to 1 or negative 1 based on the orientation, right? The converse says this. If R is here or here, it does not mean that the relationship is linear. The converse is not true, okay? In fact, it's possible to find R to be, let's say, 0.95, and the relationship looks weird, looks like almost like a parabola, okay? So I wasn't contradicting myself when I said that if the correlation, if the scatter plot looks linear, then R is very close to 1 and negative 1. And now I'm saying the converse. If the correlation coefficient is in this area, which means here, it does not mean that the relationship is linear. So the converse is not true. Be careful. All right. So this one is similar, but it's not quite the same. The correlation is only used for linear relationships. Think about that. Because you might say, well, you just told me a second ago it's possible for R to be this, and the relationship is not linear, which is true, and I did something like this. It looks curvy, and now you're telling me it only works for linear relationship. That's true. In other words, we never, ever, ever mention R when we deal with any non-linear relationship. So if you have a model that looks like this, if you have a model that looks like this, you say, wow, I found a really nice model called quadratic, and it looks almost perfect. Therefore, R is, I'm going to say stop. Don't mention R when you deal with non-linear relationships. That's what I'm trying to say here. Okay? The last one is extremely important. So what does it say? It says the correlation does not imply causation. In other words, just because there is a strong correlation between X and Y, it doesn't mean there is a cause-effect relationship. This is a mistake a lot of people make, even in talking. They confuse the two. They confound the two concepts. Just because there is an association or a relationship or a correlation, I'm speaking now loosely in English, just because there is a relationship, it doesn't mean there is a cause-effect relationship. The cause-effect relationship has its conditions. It is subject to the lab. Now, the converse is true, by the way. If there is a cause-effect, clearly there is a relationship, right? So, for example, if somebody says bad marriage or good marriage, well, that definitely implies there is a marriage to begin with, right? But just because there is marriage, it doesn't mean that it is bad, or it doesn't mean that it is good. So the stronger word here is this word. This is a very strong statement. Nobody has the right to talk about cause effects unless you have a proof. It is subject to the lab. So if you do have a cause effect, clearly you have a relationship. But just because there is a relationship, it does not mean there is a cause effect. Okay? And we will address this when we talk about sampling methods in a future chapter. All right. So these are some words on the correlation coefficients. Now, so now you know, for now you know this. You know that if I give you two quantitative variables and you know which is your explanatory and you know which is your response variable, you can easily put the scatter plot together. So that's a joke. It's like third grade. You just put the point, right? The question is, how do we get this line? Because there is no line. You can't have a line through these red dots. So how do we get this line? There are two ways to get this line. And then I'm going to show you where is this line coming from, which is the subject of today. One way to do it is to use the graphing calculator, which I'm going to show you today. Another way to do it is to do it algebraically, which I'm going to show you next time. What I want to focus on, though, today is why is this line the best line? In other words, if I have 16 students and I ask each one of you to come up and draw the best possible line you could think of that captures as many red as possible. One of you might do something like this. Another one might do something like this, just using the naked eye. Some of you want to capture as many points as possible, even if you leave some so far out. Others might say, you know what, I like a happy medium. Let me just cut across so I don't upset these people and I don't upset these people either, right? I will definitely get 16 separate different lines. But there is a mathematical way. There are many actually methods, but one of them is called the least square regression line. And oftentimes it is abbreviated by LSRL, least square regression line. So that's what I really want to explain to you today. Mathematicians came up with an idea, and it says the following. This is the main idea. Watch. Put it in black. So this point here is an observed points. By the way, I forgot to explain what this is about. So these are prices of trucks in relation to the miles they have been driven. So of course, if you have an old truck that has driven 100,000 miles, its price, well, we don't have that value, but let's say 40,000. 40,000 is probably worth around $22,000. Or maybe a truck that has been driven for 140,000 miles, its current price is $20,000. So clearly there is an inverse relationship, right? The more you drive, the cheaper it gets. Okay, the more you drive, the cheaper it gets. The two arrows flip-flop. So it's an inverse relationship. Not inverse, but you know what I mean, that the line is facing this way. In other words, the association here is negative. So let's go through the analysis very quickly. The overall shape, it looks fairly linear with a negative association because it's facing down, not facing this way. The correlation is modest, fair, bordering weak, I would say. And outliers, this is possibly an outlier, maybe not. Okay, I wouldn't call these outliers, but maybe this one, maybe none. Okay, so that's loosely speaking, that's how you would analyze this. The question is, why is it that this is the best line? And if I have 16 of you with 16 lines, I mean, obviously none of you is going to do something like this. Most of you will go in this direction, but you will definitely come up with different lines. Why is this the best line? So here is the deal. If I have a value, let's say, let me try to see if I can capture a point here. So these are basically called observed values. You know, a truck that has been driven for, let's say, 42,000 miles is worth exactly this value. This is observed. You go to the dealership and they will tell you a car that has been driven this much, this is the value. A car that has been driven that much, this is the value. These are observed values. Okay. Now, if you focus on any x value, let's just focus on this value here, this mileage, okay? So let's say it's 130,000 miles. For a 130,000 miles, the dealership will tell you this car is worth maybe $9,000. That is observed. That's what they're telling you. However, based on this line, 130,000 miles will be worth this much, 16 or 17,000 miles, based on what? Based on the regression line, based on the line. That is not observed, that is predicted by the line. So there are two y values I'm referring to. I'm referring to an observed value represented by the y value using the red dots, and then I am using another y value called predicted, or predicted by the line, and we give it a label called y hat because we don't want to confuse the observed value with the predicted value. Okay, so for instance, let me pick another one. So let's say a 70,000 mile truck is worth $21,000. That's what the dealership is going to tell you. For this car, this is how much you're going to pay. However, so this is a y value. This is observed. But according to the line, which I haven't explained to you where it came from, the value is maybe 26K. That is predicted, and this one is observed. See the difference? Clearly, there is a difference, right? And that difference between this point and that point, which is basically $5,000, that is called an error. Isn't that true? That's an error. Because that is predicted by the line, that is observed. Notice there is a, let me erase it so you could, there was a red dot there, right? That's observed, but that's predicted. And therefore the difference is called the error, or sometimes we call it the residual. It's just the error, the residue, the leftover, okay? Now, so mathematicians came up with a really nice idea. They said, look, the way I'm going to draw the blue line is the one that's going to give me the least square, or least square total square. Here's what it means. So let me work out a couple of things for you. I'll do it in green. So this is y, and that's y hat, and this is an error. This is y, and this is y hat. That's an error, and that is an error, and that is an error, and this one is an error. This is y, this is y hat. So y minus y hat is the error. Notice that this error is negative because y is smaller than y hat, right? Y is smaller than y hat. So this error is negative. Positive error, positive, 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 negative, 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 positive, positive, and so on and so forth. Now the problem is, imagine this error is 1 and this error is negative 1. So they cancel themselves out. Well, that's silly. They shouldn't cancel themselves out. I have an error of 2 actually, right? 1 up and 1 down. So mathematicians decided to do this because they don't want to deal with the negatives and positives, just like exactly the way we dealt with standard deviation. If this is, let's say, 2, they create a square that is a 2 by 2, and we're going to call it a square of 4. And if this is negative 2, we're going to create a square out of this one, and that's still going to give me 4. In other words, we're not going to cancel 2 with negative 2. We're going to have 2 4s. Make sense? In other words, we don't care about the direction of the error if it's negative or positive. We square it by creating an actual square. And let me do one more. Let's say this is 3/2. Well, 3/2, we're going to create a square out of it, and that's going to give me 9/4. And let's say this is negative 2. Well, we're going to create a square here, and we're going to call it 4. And let's say this is half. We're going to create a square, and we're going to call it 1/4. And what they did is they add up those areas, all of them whatsoever, right? All of them. And the one that gives you the smallest sum of the squares is your best fitted line. So it's called the least square regression line. That's where the idea came from. I hope you understand why I'm creating squares, because I really don't care. I don't care if it is -1 or +1. Because once I create a square now, I get a 1 by 1, which is now I have an area of 2 total, right? But if I just deal with -1 and 1, when I add them up, I get 0, as if all the points are on the line. But it's not true, okay? So that's where the idea came from. I think it's so important to know why is it called the least square regression line. And so now if I have 16 of you drawing 16 lines and going through all of those areas and creating squares and add up those areas, I guarantee you that all of your totals, some of them will be better than others. Better means smaller total, right? None of you will beat this line. If I add all these squares here, I'll get some number. Let's call it 400. And the 16 of you who come up with 16 lines, just using the naked eye, let's say, if you follow the same process, you're not going to get the sum that I just quoted. I forgot what I quoted. I think I quoted 300. Some of you might get 400. Some of you might get 1500, right? Nobody will beat the sum of the squares in here because it is done mathematically. That's why. And there are other methods, by the way, but this is definitely one of them. You probably heard about it before. It's called the least square regression line. So let me conclude with this. How do we find a line? How do we find a line? I'm not going to do it by hand because it takes time. I'm going to show you how to get it on the calculator very quickly, and then I'll finish the video. Okay? So here's how you do it. Clearly, we want the line. And that line, we don't call it mx plus b, we call it a plus bx. We don't even call it ax plus b. It's a plus bx, okay? Notice I put a hat because this is the predicted value. This is not the observed from L2. The very first thing you're going to do is go to stat edit, as you know, and you insert your values in L1 and L2. Make sure L1 has the explanatory variable and L2 is represented by the response variable. So you know how to do this. Then step 2, you click on Stat Calc and you either scroll down to number 8 or literally press the number 8 and it's going to scroll down. Thanks for you. And you're going to see something like this. Click Enter and you're going to get your values. You're going to see this on the calculator. Calculator is dumb. It's going to say y1 equals a plus bx or something. Now, even though it says y1 or y, you need to think of it as y hat, okay? Because it is this predicted line. It's not observed, it is predicted. It's not observed, it is predicted by the line, okay? Predicted means y hat. So the calculator will say y, but you need to say y hat, okay? And it's going to give you the two values, and you can just insert them. And then you can go to y equals and just graph the line, and you're basically going to end up superimposing the line on this scatter plot. We say superimpose because there is no such line that goes through all these points, is there? There is no line. I mean, they're not lined up. So we are superimposing the blue line by following these steps. Now, last comments quickly. Most of you on your calculator will see A and B, but we would love to know R, don't we? We want to see A, which is your initial value, the y-intercept. You want to see B, which is your slope, but we also want to see how, because we don't want to do this, okay? We don't want to do this. We want to get it on the TI. Here's how you do it. You click on second 0, which is catalog. It's at the bottom. Second 0 will give you catalog. Catalog is like a dictionary or a menu. You have two options. You can scroll down until you hit the letter D. It goes in order, A, B, C, D, right? Or you can click alpha. I believe it's alpha x with -1. I'll write it down. Alpha, the green alpha, x with -1 is basically the letter D, literally. So if you do alpha x with -1, it'll take you all the way down to letter D, because we are looking for letter D. And there are so many pieces, so many words in the catalog. I mean, it'll take you like 30 seconds to scroll down to D, or you just do what I just did. Now, once you get to D, scroll down a little bit to see diagnostics. Click on diagnostics on. There is off and on. Most likely yours is off. Turn it on, click done, and go back to this step. Stat calc number 8, and you're going to get that, and you're going to get that, and you're going to get that. You're going to get all of them, okay? All you need is A and B, but if you're curious about R, this is how you do it. And once you turn it on, by the way, you never have to turn it on again. It'll just be there for you every single time, okay? Unless you what is this called? You erase the memory of your calculator, then you have to start over again and do number 3. All right, I spoke enough. Take care. Bye-bye.